Сиди сюда или...
Сюда можно. Хорошо. Спасибо.
Это показывать, а вы с этим.
Да. Доброе утро. Джоу Цзюань.
Yes,
Джоу Цзюань.
Suzanne. Yes. Thank you. Please.
Good morning. May I speak Russian? Or somebody don't understand Russian? You don't understand. Okay. Joe Zhang is my PhD student, and she made details for these algorithms. The notion of isomorphism is very widely spread in mathematics, and here I will use the notion of isomorphism of two elementary conjunctions. What form is it done? I'm interested in some artificial intelligence which are connected with investigations of complex structured objects. And a complex structured object is an object which consists of some elements which are described by properties of these elements and some relations between them. It was offered about 60 years of the 12th century, but most of problems are NP-hard or NP-complete. And description of such a complex structured object is an elementary conjunction of these predicates. Okay. Two elementary conjunctions are called isomorphic if they are equal up to the names of variables, but it is very important for us to regard such atomic formula with variables, which is such that P and Q may be received from R with substitutions of its arguments into R. For isomorphism of graphs, we don't use such intermediate graph, but here it is very important. Because this elementary conjunction R describes common properties of two objects. And it is not, we say that this chair is near this chair, but we can say that X is near Y. Okay. To describe the algorithm, very important notion is characteristic of an elementary conjunction. It is for one atomic formula, for elementary conjunctions with only one predicate, characteristics describes that the first argument may be the argument A may occur n1 times for on the first place, and 2 on the second place, and so on. And for elementary conjunction with one predicate, its characteristic is a string of characteristics for every argument. Here we can see that A is 1 time on the third place, no occurrence on the second place, and 2 occurrences on the first place. And that's why this is characteristics of arguments and characteristic of all the elementary conjunction. If some elementary conjunctions are isomorphic, then their characteristics coincide, but vice versa is not true. For the algorithm, it is very important to look such structure, which we call it the structure mapping. This structure says that these variables have the same characteristics that these variables. And that's why maybe CG1 may be substituted instead of XY, but maybe this is this argument which may be substituted instead of this, and so on. And that's why we must look what is the substitution only between these arguments. And then we can algorithm we call it is ZOM from isomorphism 1, because it is only for elementary conjunctions with one predicate, only one predicate, not more. Let we have 2 conjunctions where A and B are maybe variables, maybe constants. For the formula R, we may take formula F2 with substitution instead of constants, new variables. These 2 formulas are isomorphic, evidently. And there is an algorithm. First of all, we find characteristics of these formulas. If they are different, formulas are not isomorphic. And if they are equal, we calculate the length of characteristics and fill in the structure mapping. If there is a pair that has length 1, it means that we have only that instead of X, we may substitute only, instead of X, only, for example, A3, for example. Then we may go to here and see if every pair has such length. It is evidently the formulas are isomorphic, and that's all. But maybe only one of elements of structure has length 1. It means that we find substitution instead of XY constant BY, And look further, you can see, and when we go back, where we go back, we must go up to here. We have less variables than it was before, and we can go once more here. Complexity. First items are fulfilled in polynomial time, and only these cycles in such a way we have k cube. It performs more and more and has some exponential time. Complexity is n power n or 2 power n log n. I can say that I have seen very famous problem graph isomorphism. I saw algorithms that has the same complexity. This algorithm may be implemented to the graph isomorphism problem if if we have one predicate, it is binary, and if with every literal p of xy we have p of yx, then we have a graph. If there is no such pair, this is oriented graph, and this algorithm may be implemented to the solution of this algorithm. Moreover, the problem graph isomorphism, this is an open problem for which it does not, we don't know if it is NP complete or it is polynomial. And graph isomorphism is polynomially equivalent to the problem of isomorphism of predicate formulas. It was proved by me and my son. Then we can see another algorithm when we have many different predicates. Not only one, but many different. In the description of the algorithm, we will look for such restriction. If we have elementary conjunction C, then C with index pi, we denote its subformula which contains only predicate pi. It allows us to use algorithm isom1. For example, first of all, we must change a little the notion of characteristics. Before the string of characteristics of subformula of this subformula, we write the name of predicate. And then the string of all these characteristics is characteristic of the full formula C. This is example. And there is an algorithm itself. First of all, we find characteristic is if they are different, that then graphs, then formulas are not isomorphic. We make such formula R as previously, and call algorithm isom1 for restriction of all formula to the formulas containing only Py. If it is not isomorphic, then this formula are not isomorphic, then not isomorphic. And if these two are isomorphic, I can say that sum of variables now has values, and the number of variables are less than in the initial formula. And then go to check, we put this list of constants in which are maybe substituted instead of variables into stack. And then while stack is not empty, we check one more and more times. Complexity is approximately the same as complexity for the algorithm isom1, because it is simply the sum of 2 power ne log ne. It is in the worst case because sometimes we will we find the substitution, and this slide occurs only yesterday evening after the speech of Asmik Sakakyan. I saw that when we have many predicates, we have hypergraph, and the same is and conclusion where we can implement this algorithm. I have said that we during recognition complex structure object, it was offered to make level description of classes when we say that not initial predicates, but that these predicates some subformulas, and it allows us this level. This description allows essentially to decrease the complexity of recognition of complex structure object. Then also logic predicate network. It is not neural network, but it some level recognition, and during description this network may change its configuration, and for the solving of this problem, checking for isomorphism and so on. A multi-agent description, when every agent knows some parts of an object, but can give to its elements different names, and to find what are the same elements. This I spoke about on ZIT, I think 19. Fuzzy recognition, creating ontology. These problems are all published, but there was no algorithm to find isomorphism. Thank you.
Are there any questions?
Some varieties have elementary theory algorithm solution. For example, quantitative data. Elementary theory of quantitative data is elementary algorithm solution.
What do you mean by elementary theory of predicate calculus? Predicate. Yes, no. This approach is based on the predicate calculus, but it is a very complex problem. This is an NP-hard, and we must, in order to implement this approach, it was in the 1960s years, it was Nielsen, Robinson, and many other who advanced these approaches. But all these problems are NP-hard. We must reduce complexity. Yes, but they are NP-hard. Of course, yes. Predicate calculus, for example, I like sequential predicate calculus or resolution method. They may be used, but all these problems are NP-hard. We must reduce complexity.
Other question? No, thank you again.
Second vote, please answer how.
The goal of this article is to clarify the location of some sets in the arithmetical hierarchy. We will mention these sets later. Let us remind the definition of class of sets P. We will deal with the alphabet lambda, which consists of 0 and 1. Lambda asterisk is the set of strings of elements from the lambda. Lambda asterisk is the set of strings, such strings. When we say the problem, we mean simply a subset of lambda asterisk. And we see that P is the class of programs recognized by deterministic Turing machines which run in polynomial type. Later, we will see, we'll speak about the class E with gap. Now, we continue about P. It is known that there exists the effective enumeration of sets P0, P1, where PE is not the set recognized by Turing machine which run in polynomial type. But these sets P0, P1, PE consists of the strings. But we want to clarify the location of some sets in the arithmetical hierarchy. For this reason, we need to deal with the sets of natural numbers. And therefore, we will encode the strings, encode the strings. We will encode based on the natural order on lambda asterisk. This order is linear order and we used, for example, by Richard Wagner. Here we see the mappings H1 and H0. H0 is the 1-1 mapping from omega onto lambda asterisk. And H is the mapping from lambda asterisk to onto omega. Indeed, H1 is the inversion of H0, and H0 is the inversion of H1. Now we can define the sets PE for any E for I. I P with K. And we can define the Oracle Turing machine and with K. We define these notions based on available numbering of completely enumerable sets W I, available numbering of computable operators, and available enumeration of polynomials. Now we remind the notion of P-magnetic set, which is this definition. And if the set is P-magnetic, if this set is a union of different sets such that these two sets have the same degree of unsolvability as the given set H. This well-known definition. This is the definition of the auto-reducibility. This notion was introduced by Trachtenberg. Then Wagner has proved that notion of P auto-reducibility is equivalent to the notion of P mitoticity. But looking ahead, we note that this fact is not true for polynomial auto-reducibility. We will mention about this later. Okay. Well-known scientist Ambos Swiss introduced the following notion. Polynomial P mitotic set and mitoticity, weakly PT mitoticity, and PT auto-reducibility. But Swiss has proved that if A is PT mitotic, then A is PT auto-reducible. But the inversion is not true. We represent the definition of P with cap P mitoticity and other two definitions according to Swiss definition. This is this definition. Definition 6, definition 7. Below, we see the definition of notion of sigma n set. And then the definition Well, it is the definition of the notion of sigma n completeness for any n. Definition 10 is definition of index sets. Now we can define our new four index sets. Definition 13. First index set, it is the set of numbers of sets which belongs to P with top. And similarly, other three definitions of index sets. TPM, WTPM, LTP. And results in this paper are it is proved that the index set P and P int, that is the set of numbers of sets which belongs to P with cap, is sigma 3 complete. And other three sets also are sigma 3 complete. We know that the sigma n complete sets are the highest sets among sigma n sets. And these theorems show that we found the precise location of this index set. Thank you. Oh, yes, yes. It is not the complete list because in expanded variant, more large reference list is 17 in the expanded list, 22 references. Thank you.
Falan değil. Deve estar final minus la natural.
Hi, my name is Hakkı Tamazyan, and I am a PhD student at Yerevan State University. Today I will present research work, the hierarchy of determinative sequence systems with different substitution rules. And my co-author is my supervisor, Anait Chubaryan. Okay. Sorry. The keyboard doesn't work. In this research work, we created a new proof system, which is called determinative sequent, and which is constructed on the basis of well-known Seizin's transformation. And we also proved that it's P equivalent to the resolution system R and also the cut-free sequent PK minus. On top of DS proof system, we also construct corresponding SDS proof system, which is the same system but with substitution rule, and also corresponding SKDS system. And also we highlight an interesting relationship between SK plus 1 DS and SKDS, where K is non-negative integer. And before talking a little more detailed about our new results, let's give some definitions. In our research work, we use very well-known concepts like a Boolean cube, and as a language in our considered proof system, we'll use the following logical connectives. We use propositional variables and parentheses. By saying proof, we understand a sequence, take like proof, we understand a sequence of formulas where each formula is considered an axiom or can be inferred from its previous formulas. And also the proof can be in the form of tree, in which case every formula in the proof should appear only once in the proof. And also we define a set taut, which contains all tautologies, and by taut n we understand all the tautologies that contain n number of variables. So by model phi, by this notation, we understand the size of variable phi, the size of formula phi. L complexity is the size of its proof, and by the following notation, we denote the minimal L complexity of formula phi in proof system, capital letter phi. So let's assume we have those two proof systems, phi1 and phi2, and by following the work of Cook and Reco, the relative efficiency of propositional proof system, we can give the following definitions. We can tell that phi1 simulates the system phi2 if there exists some polynomial phi where for each formula phi there exists this relation in formula phi1 and in systems phi1 and phi2. And also we can say that phi1 and phi2 are p equivalent if they simulate each other. Moreover, if we have that proof system phi2 simulates proof system phi1, and also there exists some sequence of phi formulas for which enough large n there exists this satisfies this relationship, we will tell that proof system phi2 has an exponential speed up over the system phi1. Let's talk a little about French systems. They are proof systems with propositional connectives, and which have it has an inference rules in the following form, and it's well known that French systems must be sound and complete, which means that for each inference rule of this form, every truth value assignment that satisfies the sequence of those formulas, it should also satisfy for formula B. And also proof system F must prove every tautology. And also every French system are p-equivalent to each other. PK system is denoted by the same is the same as the sequence system LK, but where the inference rules are constrained in propositional logic. So it's the only axiom is this sequence, where K is any propositional variable, and as usual, it has some inference rules, structure rules, logical rules, and also the cut rule. By PK minus, we denote the same PK system, but without cut rule. It's also known that systems PK and French systems are p-equivalent, and also for any non-negative integer k, the system PK plus 1 has exponential speed up over the system PKK. And by system PKK, we understand the system PK minus 1 with substitution rule, where the formula that we use in Kite rule is bound, its connectives are bounded by K. And our second inference proof that we use in our research work is the elimination system E. The system E is defined in the work of Ana Ichubarian, in the work of which is on proof complexity in some systems of classical propositional calculus. It's defined the following way. Let's assume we have some formula phi, which has this set of variables, and by P prime we denote it's some subset. We can also define the conjunct K, which represents just simply as a set of literals, and no variable in conjunct K appears with its negation simultaneously. So we can define, we can give the following definition for the system E. We can say that if we have the sequence of sigmas from the Boolean cube EM, and also the following conjunct, we can say it's phi1 determinative if assigning every PIG to a sigma j, the value of we can obtain the value of phi, and the value of phi can be obtained independently of the values of the remaining variables. The second definition in regards to the set of D, we can call it determinative disjunctive normal form if phi is equal to D and for every conjunct ki is one determinative for phi. The only inference proof for the system E is this one, where we can infer conjunct K prime unite with K double prime from those two conjuncts, where P is some variable. And also, as the proof system E doesn't have any fixed axioms, for each proof we can just take the conjuncts from some determinative DNF of phi. Also, to prove a proof in the system E is the following way. We say that the set D is full if by applying elimination rule we can prove an empty conjunction from the corresponding axioms. Okay, one more interesting fact that let's assume we have some variable, some formula phi, which has n number of variables. It's a tautology. And we also have that formula phi, the minimal number of variables in its conjunct is equal to m. Then we can calculate and say that the lower bound of its proof in system E must be 2 to the power of m. By using this fact, we can prove that, for example, in this well-known tautology, which is called in this well-known tautology, as its minimal number of literals in one determinative conjunct is equal to n, then its lower bound of L should be equal to the power of n. A similar example is this one. And we can say, and again, after these deductions, we can tell that its lower bound should be equal to the power to the power to n minus 1. So afterwards, let's talk about the resolution system R, which only uses the following inference rule and proves the tautology by showing that its negation is which is put into a conjunctive normal form is unsatisfiable, and we can apply Tsesing transformation on top of it and the proof if whether is some formula tautology or no. And our main proof system is the determinative sequence system DS. So if we have some formula phi, we construct its associated sequence where each subformula is attributed to some new variable, and all the sequences are constructed the following way for each of its subformula. So as the axioms, we can take all those sequences, so they are not fixed in the proof system DS, and the overall size is no more than 6 times of the size of phi. These are its inference rules, and to prove is whether a variable formula phi is tautology or no, we should just prove its corresponding sequence in the system DS. So on top of the proof system E, R, and DS, we can also construct the systems SE, SR, and SDS with substitution rule by using corresponding generalized inference rules. And we can define the same way those three proof systems. And the main results are that first of all, we prove that the system DS is equivalent to the system R. For every non-negative integer k, we prove that SKDS is equivalent to the system SKR, and also that proof system DS is equivalent to the system E. And as the corollary, these propositions are true also, that proof system is equivalent to the system PK minus, that system SKDS is equivalent to the system PKK, and also that for every k, system SK plus 1 has exponential speed up over the system SKDS. And SDS is equivalent to the system PK, and SDS is equivalent to the Frege systems. And overall, the final hierarchy of proof system can be shown in the following figure, when the top one is the most strong one. And one more interesting also result that we can prove using Thesin's transformation, we can construct some axioms from disjuncts or sequence that has no more than 6 times of the size of phi. But also, if we just consider the disjuncts from conjunctive normal form of the negation of phi, or just the conjuncts of DDNF of phi, which has exponential more larger size, the proof remains the same for both cases, the proof size. So thank you.
think about. Because this,
The title of our talk is on singular functional variables in hyperidentity of distributivity. This is a joint work with Moxie. In book 1, the classification of left and right distributive hyperidentities in binary algebras with some binary operation is proven. Namely, this theorem. If non-trivial left and right distributive hyperidentities hold in functionally non-trivial Q algebra, then the left distributive hyperidentity will be of rank 2 and equivalent the hyperidentity of the form 1. And a right distributive hyperidentity is form 2. In book 2, the Belousov Atzel problem on distributivity criterion for invertible algebras and Q algebras is solved. Namely, the distributive Q algebra Q sigma is idempotent and there exists a commutative Mufang loop such that each operation R is defined by the rule. Where phi A and psi A are endomorphism of the commutative loop Mufang and these endomorphisms are commuting. In the present talk, we give a classification of non-trivial left and right distributive hyperidentities satisfied in non-trivial divisible algebras and give the criterion for the distributivity of divisible algebras and distributivity of binary algebras with some division operation. We start for some definitions. Let Q sigma be a binary algebra and let R for element from Q and X is operation from sigma. Then define the following two mappings L, A, X, such rule and such way for R, X. We say that Q sigma is a left cancellative algebra if the mappings, these all mappings are injective and divisible if surjective and invertible if bijective for all X and A. An algebra is called cancellative if it is a left and right cancellative. A groupoid is called left precancellative if we have the following implication. And we have the first lemma. The class of left precancellative algebras is closed under Cartesian products. Hyperidentities are second order formula of the following form, where capital X are the functional variables and small x are all object variables in the world W1, W2. The number K is called the functional rank of the hyperidentity. We will say that the hyperidentity holds in algebra Q sigma if this equality is valid when every objective variables x, g is replaced by any element of Q and every functional variables replaced by any operation of the corresponding quality from sigma. The hyperidentity, the following hyperidentity is called the hyperidentity of left distributivity, and next hyperidentity is called the hyperidentity of right distributivity. These hyperidentities are called dual. The hyperidentity is called non-trivial if at least two different functional variables occurs in it. The binary algebra is called distributive if it is satisfied these two hyperidentities idempotent if satisfy the hyperidentity of idempotency, commutative for if satisfies the following hyperidentity, and hyperassociative for this hyperidentity, and medial if satisfies the medial hyperidentity. Now we present some preliminary results, but these results are interesting by themselves. First proposition, distributive algebra Q sigma is idempotent if one of the following conditions hold. Q sigma is left divisible algebra or right divisible algebra, left cancellative algebra or right cancellative algebra. And next, yes, algebra is called trimedial if each of these subalgebras generated by three elements is medial. Next proposition, every idempotent and trimedial algebra is distributive. Every distributive divisible algebra is precancellative. And from this result, we get the corollary, Kepka's result, a distributive divisible groupoid is precancellative. Next proposition, let Q sigma be a commutative invertible algebra with a common identity, in which for all x, y, for all operation from sigma, the equality is whole, is valid, where f, y is some mappings from Q to Q, depending on the operation y. Then the algebra is functionally trivial. A functional variable x is said to be singular in a hyperidentity if x occurs just once in it and at least one of the following conditions hold. A subword w involves object variables x from omega 1 and object variables y from omega 2, each of which occurs just once in w. And second, the subword W has the form. That's the form or this form, and there exists an object variable Y from W different from X and occurring just once in W, where and our first main result is the following theorem. In a functionally non-trivial D algebra with dual hyperidentity of left and right distributivity, and left or right distributivity hyperidentity does not have a singular functional variable. Next main result, if non-trivial left and right distributive hyperidentities hold in functionally non-trivial divisible algebra, then the left distributive hyperidentity will be of the rank 2 and equivalent the hyperidentity 4, this form. And right distributive hyperidentity is have the form 5. Next result. Divisible algebra Q sigma is distributive if and only if there exists a commutative Mufang loop such that each operation R from sigma is defined by the rule, where F, A, and GA are surjective endomorphism of the loop Q, which is commute. And we have the following identity. And this element is from a nuclear of loop Q. And Q is this nuclear of loop Q. Corollary. As a corollary, we get the following statements. Q sigma is medial The following statements are equivalent. Q sigma is medial distributive divisible algebra. First. Second, Q sigma is medial idempotent divisible algebra. And third, there is an abelian group and system of surjective endomorphism, which is commute, and every operation have the form. A binary algebra Q sigma is called a D-algebra if sigma has a divisible operation. Lemma. In the distributive D-algebra Q sigma with a divisible operation R, the following second order formula is true. Second lemma, a distributive D-algebra is idempotent. The next, the distributive D-algebra Q sigma is idempotent, and there exists a commutative Moufang loop Q such that R from sigma is defined by the rule where phi and psi are endomorphism of the commutative loop Q, and this endomorphism are commuting. It's all. Continue next.
It is not working. No. Use the mesh. Yes, that's it. Hello, my name is Nazani Shahbazi. I am truly happy to be here with you today. I'm a last year master's student conducting my research at Al-Azhar University, Tehran, Iran. I had the privilege of working alongside my co-author, Mohammad Reza Keyvanpour, from the same institution. I work in the field of automated software testing, and today I'm here to present our research on automated model-based test case generation for UML activity diagrams using EFSM. Software development, especially for complex systems, is prone to a lot of human errors. Software testing plays a crucial role in identifying errors and is a vital but costly phase in software development process. To address this issue, we use automated model-based test case generation. Software testing helps us identifying errors, and one significant challenge in software test case generation lies in the generation of test cases, which plays a crucial role in identifying errors and helping the testing process. To address this challenge, we turn into modeling techniques. Model-based techniques are techniques that are centered around modeling the behavior of the system for generating test cases and testing the software behavior. These techniques are black box approaches, eliminating the need for the source code and helping us to reduce the testing time and effort. When talking about modeling the system behavior, UML diagrams are one of the models that we can highly use and are highly recommended. They are popular software modeling options. One of the most used modeling diagrams in the context of model-based testing is UML activity diagram. However, although their popularity, there is a lack of automated techniques when using UML diagrams. Formal models are one of the ways that we can address this issue because they mitigate UML activity diagrams by generating formal specification for behavior in the behavior of the system. EFSM is one of the most used formal models in the context of model-based testing, but however, there are a lot of advantages. They are rarely used in practice due to developers' lack of training and knowledge. In the context of this paper, we produce an approach that maps UML activity diagram meta model into EFSM meta model. Then we have an EFSM-based method to generate test cases. Generated test cases are evaluated afterwards. UML activity diagrams allow us to model the dynamic characteristics of a system. A UML activity diagram is formally defined by a 6 tuple, where A is a finite set of actions, T is a finite set of transitions, F is a finite setup that shows the flow from activities to transitions, C is a finite set of conditional guards, AI is the initial activity state, and AF is the final activity state. Elements used in our study are initial node, final node, executable activity node, merge node, decision node, input and output pins, and send and receive signal actions. Extended finite state machine is a well-known formal specification technique that defines various states and elements acting through a software. It is formally represented by a 6 tuple, where S is a finite set of states with S index 0 as its initial state. V is a finite set of vertex, I is a finite set of input transitions, O is a finite set of transition outputs, and T is a finite set of transitions. And numerous research studies has been conducted on this research. Some of the most relevant are the one that we're going to talk about. One of the most relevant related works on this area uses UML sequence diagrams and EFSM for generating test cases. One of the weaknesses of this approach is that it works only for sequence diagrams. We built our work upon this approach, but we extended it to work with activity diagrams. Using activity diagrams helps us to generate test cases for more complex system behaviors. In another study, authors proposed generating scenario-oriented test cases using UML activity diagrams. Their approach consists of converting the UML activity diagram into a UML activity dependency graph, and then test cases are generated from the graph. In another related study, generating test cases using both UML and sequence activity diagram are proposed. The approach involves conversion of sequence diagram into sequence graph and activity diagram into activity graph. However, this work shares similarity with ours, but it diverges by not using MDE concepts, formal models, and moreover, it necessitates the generation of 2 manual UML diagrams, which make it complex to use for complex systems. In our proposed approach, we map UML activity diagram into EFSM diagram. We use this by defining a newly defined UML activity diagram meta model, simplified rather than the UML formal specification, then use an EFSM-based method to generate test cases. Afterwards, we use model JUnit and JUnit to utilize the generation of test cases. Axelio is then applied for a 4-step automated approach to execute the test cases and convert them from a model representation into a textual representation that can be executed. To present a simplified foundation for our work, we have defined 2 meta models, one for activity diagram and one for EFSM. The formal UML specification has been heavily criticized because it is hard to navigate and complex to understand. So simplified meta models are very common in this literature. So in this study, we propose a simplified version of the activity diagram meta model tailored specifically for simplicity while ensuring close alignment with the EFSM used in our study. As you can see, our activity contains of activity edges and activity nodes. Activity edges can be of type of object flow or control flow. Activity nodes can be of type of action, control, or object. Control nodes itself can be of type of initial, final, decision, merge, join, and port, and object nodes are a kind of activity parameter nodes, which are pins. Pins can be our input or output. Decisions can be of type of switch and conditional. For EFSM meta model, there is a formal specification for this meta model containing of 6 meta classes. There is an EFSM class having a name. Each EFSM has initial states, some states, context variables, and transitions. Transitions have name, input, output, event, guard, and action. The states and initial states come from an abstract class that has only names. Each transition has source and targets. Each EFSM has only one initial state and multiple transitions and context variables. Then we propose some transformation rules, transforming the earlier discussed activity diagram meta model into the EFSM meta model. These transformation rules contains of 2 kinds of rules, normal rules and lazy rules. Lazy rules are called multiple times during the implementation of normal rules. The first normal rule is initial node. It operates for initial node, creates S index 0 as its initial node, then it increments the order of I, and afterwards current state and previous state are updated. For decision node, it operates in 2 stages depending on the type of the decision node. For the decision node of type conditional, it creates 1 new state, 2 new transitions. With the transition of guard true, it goes to a newly created state, but with the transition of guard false, it goes backward to the previous state. For the rule of node merge node, it operates for merge nodes, creating transitions for each of the edges that go to the merge node and 1 new state. All the transitions go to the state. For nodes of type signal or action, the 4th node works. It handles signals and activity nodes, creating 1 new state and 1 new transition. It also checks if there is a transition going backward without any guards. If such transition exists, it will create a new flow and will guard it as it has it. Lazy rule initial state generates S index 0, incrementing the order of I. It also saves the name of the activity in a variable. Lazy rule state generates a new state, increments the order of I, updates the previous state and the current state. Lazy rule transition establishes a new transition connecting the previous state to the current state, incrementing the order of J. Then we implemented a 4-step automatically generated Axelio to transform the model transformation into textual transportation. After that, we used ATM as our case study, implementing all of the steps described earlier. The results obtained are all reported in the table. Generated test cases, state action and transition coverage metrics, and the execution time. As you can see in the table, our execution time is under 1 second. Transition, state, and action are fully covered. Our approach's main novelty lies in its ability to automate the entire testing process with the exception of manually defined stubs. We achieved complex coverage metric, as already mentioned. We have an execution time of under 1 second. All of these show that our approach is applicable and efficient enough. And no other work has reported the same level of automation using activity diagrams. Since there has not been such work with the same level of automation, it's important to note that direct comparison between works with different levels of automation are not valid. So we can compare our work in a more general way. To further illustrate the level of automation we have achieved, we had a table with 3 of the most automated approaches already done in this subject. The approach with Enrosha ETL have a level of automation of very high. It automates the entire testing process, but it's not applicable to ABs. So we cannot use that. The second one has a moderate level of automation since it generates test data manually from automated generated test scenario. The article by Melina is fairly high. It is automated, but it necessitates the generation of 2 UML manual, which makes it complex to use. Our approach has a level of high automated. It automates the entire testing process. Only stubs are generated manually. In conclusion, we proposed an approach that fully automated the generation of test cases for UML activity diagrams. We use formal models and model engineering concepts. We proposed a simplified activity diagram meta model that is both simple and applicable. We achieved a fully coverage metric and execution time of under 1 second. And we applied a 4-step approach using Axelio to transform our model representation of test cases to a textual that can be executed. To further illustrate our work, other UML diagrams can be incorporated into our study, like state diagram or activity diagram. Advanced techniques such as mutation testing can be incorporated, and our approach can be applied to a real-world application to further illustrate the applicability. These are some of the references, and thank you so much for your attention.
Yeah. Thank you for the presentation. Do you consider involving generative AI? We feel that
It does use AI, and the algorithm is AI based. It is a look ahead forward algorithm used in Model JUnit tool itself. So I didn't implement the algorithm, but the algorithm is inside the tool which I use to execute the generated test cases, and it is an AI, so I could automate it. Yes. Thank you very much. Yes. Yes, yes, yes. All coverage metrics very complete. Coverage is a measure to show us how much of the code and source code. I'm testing a source code. I want to make sure that my source code is working. Yes. Yes, it is fine. Yes, it is. It is a source code. I'm testing it, but since 2000, it has been done manually. But now it is automated. We want to make sure that the AI.
What is corporate text?
Yes, yes.
What is it?
Coverage. It means
Coverage.
I covered the whole package. Let me show you. On the graph, yes. It is a graph. It is important to cover all the states. I'm testing. I want to make sure all of the methods are running exactly the way they are supposed to.
Okay.
So cover.
Thank you. No.
Thank you. Can I just take that? Thank you very much.
Não, não, me pediu como que.
Sim, ó.
Ah, tá. Menek. Oké, menek mungkin kok sekarang masih. Hala, очень. Hi everybody. I'm Anna Gebrusyan. I'm a former student of American University of Armenia, and I'm gonna present you a work done with Professor Automata on a topic of string classing using the fuzzy context free pattern. What we will talk today about? I will formulate the problem, then we will talk about some applications. We will go on and talk about some basic definition. Then we will solve the problem and talk about the analysis, the complexity, how fast it solves the problem. Okay, what is the problem statement? We want to say the degree to which a crisp string belongs to a fuzzy context free pattern. A crisp string is the string that you all in your loop. It's just a string, fuzzy. It is finite number of elements. But the fuzzy context free pattern, I will define this later. What is it? Two application areas that I want to mention are bioinformatics and natural language analysis. Let's talk about this in more detail. What we do in bioinformatics, there are some prototypes. Prototypes are some groups of DNA sequences which are similar to each other, and each sequence has a belonging degree to that group. And then we have different prototypes, and one crisp string, which is also the DNA sequence, and we want to know how much to which prototype this string is closer, much closer. So to answer this question, we can just represent the prototype and the context free grammar, and then solve the problem of belonging degree of the string to the fuzzy context free grammar. Same for the natural language analysis. Assume we have a set of concepts. Concepts are some ideas which are described with a group of words. Each word has a belonging degree to the concept. Like if and we have another word which is our crisp string, and we want to understand in which group this word belongs to most. To do so, we can also represent the concepts as the fuzzy context free grammars and solve the belongingness to the program. Okay, this much on the applications and the problem statement. We are gonna give some basic definitions which we have to give the problem in a mathematical way. What is the fuzzy subset? Let's start from the crisp subset. What is the crisp subset? Let us have a universal set and the subset. What we can say? An element from the universal set can belong to X or not. So the belonging degree of any element can be 1 or 0. And if we have a fuzzy subset of universal set, the difference is that the belonging degree of any element from U can be from the segment of 0 to 1, not only 0 or 1. So also can be 0 or 1. Okay. I will press. What is the fuzzy context free grammar? It's just a fuzzy grammar. Just with one difference, derivations have degrees, and when we get a word, it will from this grammar, it will have a degree, which will be the matching degree of the word to the fuzzy context free language, which was the result of this grammar. But what we do, we don't have just fuzzy context free grammar, but we have fuzzy patterns which are based on the fuzzy symbols. Fuzzy symbol one is a fuzzy symbol. Fuzzy symbol is just a fuzzy subset on an given alphabet. For example, if we have an alphabet 1, 2, 3, 4, 5, we can define a fuzzy subset, fuzzy symbol on this alphabet. For example, S as a small number, and 1 will certainly belong to this subset because it is a small number, and 5 will certainly not belong to this subset because it is not a small number. And these are some examples of fuzzy symbols. These are not all of the fuzzy symbols, but just some examples. So, what is fuzzy linear pattern? It is just a string which consists of fuzzy symbols, not ordinary symbols. So, if we have two things, fuzzy linear pattern and free string, we can find the matching degree of free string to the fuzzy linear pattern if we accumulate the matching degrees of each member of these strings. Accumulation operation here we define the multiplication, but it can also be for the minimum. What we want to do, we want to work with fuzzy context free pattern, which is the group of fuzzy linear patterns. It's a context free grammar. The difference from the ordinary context free grammar is just that the terminal symbols are fuzzy symbols and not ordinary.
Say your result.
The result is that if we have a free string and we have a fuzzy context free grammar, we can, if you want the result, okay. The result is if we have a fuzzy context free grammar, a fuzzy context free pattern, and free string, we have an algorithm which defines the membership degree in all n q times p plus q, where n is the size of the string, p is the size of the pattern's derivation number, and q is the one that was added.
What is CYK?
CYK algorithm is Hodlinger-Raskin algorithm. It's a known algorithm for belonging degrees, but this is qualified CYK algorithm. What? No. It takes the fuzzy string. It takes the Chris string and creates the triangle table, and here it's normal was yes. What is that? It is in the top here we have the material.
Regular language.
I don't really know the algorithm to compare them.
Okay, thank you. Excellent.
Thank you. There's